All right, my friends, welcome back to Build Science
201.
We're talking thermal control, and this episode is specifically about
Resistance, a measured value.
All right, guys, let's get going.
Build Science 201 is sponsored by Anderson Windows and Doors, Huber Engineered Woods, and Proseco. This episode is brought to you by Rockwool.
Hi, everyone. I'm Matt Reisinger, and today I want to talk to you about a brand that has a remarkable 120-year legacy in producing quality, performance-focused products. That's Anderson Windows. In the South, especially here in Texas, that legacy really comes to life with the Anderson 100 series. Gosh, I think I started using this line when it very first came out, and from the beginning, I have really liked this window. This line enables you to choose dark colors without sacrificing performance. That's right, style that doesn't compromise on quality. One of the key features of the 100 series is Fibrex, Anderson's proprietary material. It's actually 2 times stronger than vinyl, which means you won't experience flex over time. Your weather stripping stays tight, and that's going to ensure that both air and water performance, water holdout that is, remain top notch. Now let's talk about performance enhancements. Anderson is expanding their triple pane offerings, which is a fantastic option for energy efficiency. You can find triple pane windows available in the A series, a FIAS certified E series, and now even in the 400 series at select locations. So whether you're looking for style, strength, or energy efficiency, Anderson has you covered. With a commitment to performance that you can trust that these windows are going to stand the test of time. Thanks for joining me today, and if you're considering new windows for your home, definitely check out Anderson and see the difference for yourself. All right, Steve, I noticed your first slide. It looks a lot like a cooler I saw you cut in half. I love this cross-section. What can we learn in this particular topic from this cross-section?
Resistance, hot to cold.
Yep. So the ice is inside, and that insulation is providing resistance to heat flowing into the cooler and melting the ice.
And melting the ice.
Yep.
But I think the big thing here is notice continuity.
Nice continuity. And we talked in a previous episode about the gasket that's on there and why they do such a good job of air sealing. If that lid was up, it wouldn't be so good at
you'd have a cooler full of water.
Exactly.
You'd have a fish tank.
But ultimately, it's that resistance. So let's keep going as we think about this resistance to heat transfer. So here's my house, actually my daughter's bedroom. And interestingly enough, some of this insulation is actually used for sound purposes. So that back wall there that has QR on there, that stands for Quiet Rock, and that's a wall that I'm doing some soundproofing on. The exterior wall I'm insulating against thermal transfer. Kind of funny, I didn't even think about it when I pulled this slide, but you know, I eliminated a window. On that wall, and I left the header in place, and you can see the jack and the king studs are still there. I could actually put that window back in someday, but you know why I'm not worried about that, Steve? Even though I've reduced greatly the R value because I have much less rock wool in there, it's because if you saw some of the other photos, I have 2 inches of exterior insulation continuous on my whole house.
Right.
So in other words, I'm not worried about that missing insulation at those solid headers. Those are uninsulated headers, because I've got this continuous blanket of insulation on the outside of my house.
So you're telling me you live in a Yeti cooler?
I basically do. An analogy that I've used a bunch that I really like, that I stole from Joe Stiebrick, is, you know, if we're cold and we're going outside, would we stuff insulation in between our ribs, or would we put a big jacket on? And not only would we want a jacket that was warm, but we want a jacket that was airtight as well. If we're skiing down the slopes and we have a big sweater on, that sweater, if it's air permeable, is not going to keep us very cold as we're shushing down the slopes. But then I put a rain jacket on top of that, and all of a sudden, I'm good to go. Okay, Steve, so this is a window sticker. Break down for me, if you would, why we think about insulation as an R value, but a window, when we talk about thermal transfer, is rated in a U factor.
Right, so 0.33 is the U factor. I'm just going to write that here. So the R value is basically 1 over 0.33, and that equals R3, right? Now, the reason why we don't have R values on windows and we have U factors is windows are multi-components,
Yep.
right? So if I just did a really quick sketch here and I say I have 3 components to something, as energy moves through this, the energy might differ how it moves through that.
Right.
So I have to do the U value of each of those, compile the U value to actually get the overall U value of the system.
In other words, the overall thermal resistance of the whole assembly.
Exactly. So you'd have U1, U2, and U3, and those equal the U value. That's why you never see R value there, and you actually have to do the reciprocal after they do the math.
Gotcha. That makes sense.
But understand the U value, the lower the number, the better, because it is the reciprocal, right?
You know, it's interesting. I didn't think about this as we were preparing, but it makes sense to me that we should also be thinking as builders about the assembly values of our walls
Yes.
too, right? Because if we just have cavity insulation and nothing outboard of that, then, you know, all of the other things are bringing down that R value. So when people say, oh, I've got R13 or R21 at my house, that's not really true, because the assembly in a combination between drywall, between the exterior sheathing, between the studs, has a different total number, total assembly number, and it's typically going to be much lower than that R value. That
Yeah, we have some slides. We'll get into that. We'll get into that chat, but it's very much. That's why I use the words component and not talked about it.
That's great.
All right, so we're going to start out here. This is a slightly exotic slide. So this is an ICF, and that stands for insulated concrete form. Basically, we have insulation here, we have insulation here, and then we put concrete in the middle.
Yep,
right?
and so the rebar is in there, and there's some plastic pieces that allow us to screw to that, but the form stays in place after you're done pouring.
Yeah.
And so now you've got a wall that has that's basically pre-insulated, right?
Yes, and so we have that R value is instilled in the formwork. You'll pull off some of these little panels here that hold the joints together, strip the bracing, and then you have your foundation wall, and it's already insulated, and it's insulated on both sides.
Yeah, that's cool.
This is another variation of a wall system. This is a thermally broken engineered stud, right? So you have an outer cord here, you have an inner cord here, you have a bunch of intermediates. That gives you, you know, somewhere around a 97% thermal break.
Oh, interesting. So in other words, if we use a total fill insulation, a spray foam, or maybe a blow-in, it fills in between that front and the back solid member, and that's how you get that thermal break on there.
And
That's cool.
coming into the corner here, Jake and I coined the Missouri corner, because people know it as California corner, but when we're using these engineered studs, we call it a Missouri corner. So.
Yep.
Double wall construction. So this is a good friend of mine, Farley's house, and you can see we have an outer wall 2x6, inner wall 2x4. If you're wondering why the outer wall is a 2x6, this is on Martha's Vineyard. It's in a very high wind zone near the ocean, so we needed that structural integrity of the outside wall, especially given this is a 24-inch on center frame.
Oh, wow.
Right. So, but, you know, double walls, we're probably talking 9, 10, 11, blown cellulose. We're probably in like an R50-ish range.
That's pretty good.
For that wall. Yeah. And it's a passive house.
With a nice thermal break in there too between those two inner and outer walls.
Yeah. So it works very, very well. So another project, Farley, this is his guest house. We did this one actually first, but notice that we hung 14-inch floor trusses on the outside of the wall. And this is when FIAS, or Passive House, was in its infancy. So they didn't really have their math climate tuned. So there was a big penalty for small houses built in the country, and, you know, different climate zones got penalized in different ways. But the result is, you know, this wall here is probably somewhere around R74, I believe.
Oh my God.
So it's pretty high.
Yeah, that's better than your cooler example, that's for sure.
I mean, Farley's lived in this house now for probably about 3 years. I think his total run time of his Mitsubishis in here for heating anyway is probably something around 2 weeks,
Oh
3
my
weeks.
gosh,
Yeah,
wow.
it's body heat, the cable box, the refrigerator, they all contribute to heating this house.
Showers, cooking, all that stuff.
Showers,
the
all
dog.
of that stuff. So there's, we can build really good houses if we want to.
Yeah, we can.
This is just another house where this is an insulation package where they have a total of 6 inches of rock wool out there. So you're at what, R24-ish plus,
That's nice.
plus or minus, and it's continuous,
Mhm.
right? So the whole idea of any studs back here, we don't really care because this system's fully thermally broken.
That's really nice. I know this house, Steve, the Build Show original house.
There it is. And, this one here is, I put this slide up here because I thought it was really interesting. Up until now, we've been doing a lot of talking about walls, maybe a little bit of floors, but here we have what I would call a floating floor or above grade floor system here. So your wall comes down and then turns into the floor, and we built the floor just like we built the wall.
It's really nice.
Right? So we have zip R9 here, and we have the same R9 here, but the difference is this also has 16 inches of blown insulation in there.
That's really cool.
And the clients have lived in here for a couple of years now. No thermal complaints. They absolutely love their house. So you've been to this house too. This one's just south of here. And there's not a lot of magic here. This is just showing kind of a standard detail of mine where we have a 2x6 wall.
Mm-hmm.
And then on the outside here, we simply have R6. And that's 1 inch of polyiso.
It's bonded to zip system sheathing, and you can see the logo right there. They call that Zip R sheathing.
Right.
And it provides a nice thermal break. And the nice thing about it is it's installed by the framers at the same time.
And it's one trip around. And in Texas, this works very well because we don't have the colder temperatures here.
Mm-hmm.
Up by us in New England, climate zone 5, that 1 inch is borderline tipping point for a 2x6 wall, meaning we wouldn't want to do R3 here.
Up in New England.
Up in New England.
Yeah.
You get away down in Texas, but this really wants to be R6, but it would be far more favorable to be R9.
R9 plus. And the further north you go, the more we want a greater amount of insulation on the outside than the inside. The reason being is we want to warm up that sheathing to make sure that if we did have a problem in our assembly, that we wouldn't have a cold condensing surface, that if moisture migrates through that cavity, especially in a cold climate where it's real cold all winter, we don't want that moisture finding a surface that's cold and condensing. And I've seen lots of photos from Building Science Corp with test walls and with walls that didn't have any exterior insulation that have actually had condensation and problems because of that condensation, because they didn't have enough exterior insulation on the house.
And it's a good point, that you make as you move north. One of the things that I do is after climate zone 5, I start rethinking the wall assembly pretty drastically. We're doing one in South Dakota, which is climate zone 6, but it's a pretty high 6.
Oof.
But the exposure it's in the middle of a field. And the homeowner's like, Steve, we get 50-mile-an-hour winds here in the winter.
Holy cow.
And I want the best house you can give me.
When it's 0 degrees out of 50 mile an hour.
So I don't want to throw a teaser out, but if you come to 301, where we're going to do it at Build Show Live, I'm going to be revealing what that wall is. And it is bomber.
That's awesome. And we're also going to be videotaping 301 before too long. So stay tuned for that next series, of course.
Now, sometimes people want alternatives to their insulation, right? So this is Havelock wool. It's a sheep's wool.
Interesting.
You've been to, this is the Hilltop
Oh,
house.
yeah, that's right.
Right?
I wasn't there during installation.
We used it on a large portion of the house. The homeowners didn't want to have any blown fiberglass or anything in there. They wanted something more natural. So it carries about the same R value, but man, I could stick my hand in there. I could rub that stuff all over me and you'd be just fine.
No, that's
so
neat.
There's a lot of alternatives out there, but check their R values so that you make sure that you're comparing apples to apples.
Yeah.
This one here, this is a detail that I put up as kind of a foil to the next detail in that, you see this a lot. Framers, we just ask them to do an insulated header.
Mm-hmm.
This is XPS, which is extruded polystyrene, and it's probably 2 inches sandwiched in that header to just provide that thermal break across this wall system.
Yep. Yeah, where there normally wouldn't be any thermal break.
Right. So this is a garage ceiling detail, very much like your house where you have a garage above. We're up here, climate zone 5.
Where I've got living space above.
Living space, right. And we want to make sure that we're providing that comfort because, again, this is a floor, right? So we insulate it here, you can see, and we're probably 12 inches of cellulose there. So let's just call that roughly R50 there. But the important thing is we have a lot of thermal bridging happening here. And so the way we eliminate that is we put 2 inches of polyiso, very much like you did at the floor in your house, and we put that underneath it. And now we have that continuity. And if you haven't seen that video, go check it out there. And that's across so that we eliminate those thermal bridges.
That's good.
This is down in the basement, right? So we've often talked about turning up that insulation at the slab. Well, this is just what happens up above. A lot of times we'll hold those studs off and we'll just spray 2 inches of closed cell there. But in this case here, the homeowner had an aversion to spray foam. So we moved to a hard, rigid insulation product here, which was 2 inches of Halo's Subterra.
And that's a GPS foam,
And
if I
it's a
remember
GPS
correctly.
foam. Yes, it is.
So, Steve, why are we showing an exterior finished house when we're thinking about thermal transfer here?
Yeah, so let's use the analogy that we talked about in episode 1. If we don't want a house to leak, we don't let it see water. If I don't want a house to warm up, I don't let it see sunlight.
Ah, so we're talking shading.
Shading devices, right? So we minimize, remember my EEM, emphasized educational moment, hot to cold.
Yep.
That sunlight is going through this glass. It's going to heat up that room pretty immensely.
Yep.
Put a shading device on the outside. Shading devices on the inside do not work because the heat energy is already through the glass and it's in the room.
Yeah, so they work to make it less bright, but they don't do anything for heat transfer one way or another, either in or out, really. It's interesting, 2 things I wanted to mention about this. We do this a lot in the South. It needs to be done with some caution, and I think it's interesting how your trellis that you did out there still actually filters quite a bit of light through there. Whereas if you had a big awning, and especially a deep awning, it could make that basement space dark. So there's this play between, I need some light in the space, but I also don't want direct sunlight, especially true for us here in the South. The other thing that I think is interesting that I want to mention was when we've traveled around the world, other countries besides the U.S. do a lot of exterior shades, and it's honestly fairly rare for us, with the exception that down here in Texas, it gets so darn hot. I see them retrofitted a lot on houses, especially houses that people just don't quite know how to cool down this particular room that's facing south and west. So they end up putting an exterior shade device on in an attempt to slow down that heat transfer through the glass. And remember, glass does have the ability to reject some of the heat. There was 2 numbers on that glass we looked at earlier. There was U factor and there was solar heat gain coefficient, SHGC. Solar heat gain coefficient says how much of the sun's heat am I rejecting? So down in the South, we want a low SHGC. I think that window was around a 0.2 or a 0.22, which means that if it was a 0.2, it's rejecting 80% of the sun's heat off that window, but still 20% getting through can make it darn hot. I mean, if you're sitting out in the sun, even if you've got a little bit of that heat off, it's a whole lot different than standing in the shade, right? If you have a tree totally blocking the sun from touching you, you're way cooler than you are standing in the middle of the street with the sun baking on a July day. So shade devices on the outside make a lot of sense. And I think it's interesting that I sense that we'll start seeing more and more Texas-based homes thinking about exterior shading in the planning and architecture phase rather than the, oh shoot phase, I built this house and it's uncomfortable.
I'm going to nerd out on you pretty heavily
Okay,
for
let's
about
hear it.
30 seconds.
All right, let's go.
You're gonna love this
I love it.
because there are some assumptions when you look at this photo, and we're gonna clear them up.
Okay.
All right, this is a passive house.
Okay.
It's in climate zone 5.
Mm.
So what does that mean? It means in the wintertime, my sunlight is at about 13 degrees.
Okay.
In the summertime, it's at, I don't know, probably somewhere around 75 degrees.
The sun is higher in
The
the
sun is
sky.
higher. I actually did the calculation of each one of those ribs and made sure in the summertime that window was fully protected at 75 degrees.
You're right, that is nerdy.
The other thing you're going to love, it's removable.
Oh, very
So,
cool.
Around September, the homeowner takes it off.
Huh.
We move into heating season, and that full 13 degrees
Ah,
gets full access to the glass. So that's a climate-tuned louver.
that's pretty neat, which we'll get into this in later phases, but that also means that we might choose a different window for a Boston house than we would an Austin, Texas house, because in Boston, we might want a little bit of heating from that sun, so we might choose a different solar heat gain coefficient number. There are even folks that will change the numbers based on the which
Orientation.
direction, the orientation the house is facing. So the south wall might get a different type of glass than the north walls.
Yeah,
that sort
these
of thing.
these were 0.55.
Okay, solar heat
For
gain
the-
coefficient.
yes.
Yeah, so very different than what I would use in Texas,
There you go.
where I want a much lower number. I'm looking for 0.18, 0.20, something like that on solar heat gain coefficient. Steve, we're almost done with thermal. We got one more module left when we talk about thermal control. What's our last module?
Proportional.
Proportional. All right, guys, with that being said, we'll see you next time on The Build Show.
This episode was brought to you by Rockwool. Build Science 201 is sponsored by Anderson Windows and Doors, Huber Engineered Woods, and Proseco.